Welcome to this video on series. We're expanding compound functions using the Maclaurin series that we saw in the last video. So what we're going to do here is we're going to use the Maclaurin series that we've got, particularly the ones in the formula book for e to the x, ln of 1 plus x, sin x and cos x, to get expansions in terms of x, series expansions for more complicated expressions. So we'll switch to the visualizer and I can show you what we mean by that. So here is the formula book. It's very important to get to know where these things are in the formula book. So these expansions for Maclaurin's and Taylor's series, they're in two places actually. They're in the AS further maths section, but here I've got them on page 18 of the formula book in the A-level section. You can use them from either place, of course. And what we're going to do is we're going to look at this first example here. We're going to expand cos of 2x squared, and we're going to use the Maclaurin series here for cos of x. So I'm just going to slide that up so we've got a bit more space, but we can still see that there. So we're going to say cos of 2x squared is equal to, well, we're going to use this, but in place of x, we're going to put 2x squared. Be careful to put it in brackets so you don't make mistakes with powers. So we've got 1 minus 2x squared over 2 factorial plus 2x squared to the power of 4 over 4 factorial minus 2x squared to the power of 6 over 6 factorial. And that's as far as we need to go. It says write down the first 4 non-zero terms. So we can do that like that. And we're going to just simplify those. Often a question will say, giving each term in its simplest form. It doesn't say that here, but I think it's good practice to do so. So we've got 1 minus, here when we square the x squared, we're going to get x to the power of 4. Square the 2, we're going to get 4. 4 divided by 2 factorial is just 2, is 2. So we've got 2 x to the power of 4 plus, this is going to be 16 over 24, which is 2/3 x to the power of 8. If you can't do these fractions in your head, just do them on the calculator. There's absolutely no reason why you need to be able to do them in your head. Although it can be useful to do them in your head and check on the calculator. Minus, and again, this is going to be 2 to the power of 6 is 64, 6 factorial is 720, and that simplifies to 4 over 45 x to the power of 12. So there's our first expansion. Let's go down to the second question here. Find the first 3 non-zero terms of this expansion and state the values it's valid for. So we're going to say, first of all, we're going to use the laws of logs. So we're going to say ln of the square root of 1 plus 2x over 1 minus 3x is going to be equal to, well, we've got ln of the square root of 1 plus 2x, which is a half ln of 1 plus 2x, ln 1 plus 2x, minus, because this is on the bottom, divided by ln of 1 minus 3x, 1 minus 3x. And now we're going to expand each one of these using the expansion for ln of 1 plus x, which we saw previously and which is also in the formula book. So let's just go a bit further up there. There we are. So this is going to be equal to a half of, so instead of x in our expansion in the formula book, we've got 2x. So I'm going to a half of the expansion of ln of 1 plus x is x minus x squared over 2 plus x cubed over 3 and so on. So this is 2x minus 2x squared over 2 plus 2x cubed over 3 minus 2x power 4 over 4. Now, I know it looks like I might have gone a little bit too far there, but actually sometimes it can be useful just to have one more. Sometimes the terms cancel out. So when it says first three non-zero terms, you might end up with this one cancelling out. So it can be useful to go a little bit further. So then we're going to say minus, and this is going to be, instead of x, we're going to have minus 3x using the same expansion. So it's going to be minus 3x minus 3x squared over 2 plus minus 3x cubed over 3 minus 3x power 4 over 4. So now we're going to simplify that. So we're going to say, well, let's look at x. Well, we've got positive x there. We've got positive 3x there. So that's 4x. The x squared, well, we've got a half of minus x squared there. So minus a half x squared. This is going to be, there's a negative there and negative there, which makes positive. Squared is going to be positive, so this is going to be plus 3 over 2 x squared. Is that right? So we've got so this is minus x squared. This is plus 9 over 2x squared. So minus x squared plus 9 over 2x squared. Let's look at x cubed. This is going to be 8 over 3, but times a half. So 4 over 3x squared. So plus 4 over 3x squared. This is negative 27x cubed over 3, which is and then we've got a negative here, so it's going to be positive 9x cubed, I think. Actually, let's leave it as 27 over 3 because we've got over 3 there. That should be cubed. Plus 27 over 3x cubed. We can probably see that none of these are going to cancel, so we can ignore that x to the power of 4 and simplify to 4x plus 7 over 2x squared plus 31 over 3x cubed. So those are the first non-zero terms. So in fact, we didn't need to go as far as the power of 4 there. Now, we're just going to answer what this is valid for. So the expansion of ln of 1 plus x is valid for x between -1 and +1, not including -1, but including +1. So the two series are valid for, well, here we've got 2x, and it's valid between 1 and -1. You see I've got an equal to there. And the other one is also -1 to 1. And this time we've got -3x in here. Now, what does that mean for x? What's the most restrictive? Well, if we divide by 2, we're going to get a half and a half, minus a half and a half there. We divide by 3 here, or -3, we're going to get 1 and -1 there. So we want x, sorry, we're going to get a third, minus a third and a third. So we want x between minus a third and a third. And we're just going to think to ourselves, well, can it be equal to either of these? Let's look back at our original expansion. If we allow x to be equal to a third, we're going to be dividing by 0, so that can't be correct. Another way of looking at it is if we put a third in there, we're going to be trying to find ln of 0, which is undefined. So definitely can't be equal to on that end. What about on this end? Minus a third. If we put minus a third in there or minus a third in there, we're going to get 2. That's okay. Minus a third in here is going to be positive. That's okay. Same thing here. So we can let it be equal to minus a third. Okay, so there's the first two examples. Next example we've got on the next page. So here we're told that terms in x to the power of n, where n is greater than 4, may be neglected. So we need to consider anything with powers of x up to and including 4, but not above that. Use the series expansions for e to the x and sine of x to show that e to the sine x is equal to this expression. Now, one way to do this would be to use the general Maclaurin series expansion. So we would say f of x is equal to e to the sine x. We would find the first, I think we need the first 5, the first 4 derivatives, and evaluate them at 0 and use those in here. So we need to, when we differentiate, use the chain rule and the product rule. But an easier way to do this is to use the expansions that we know already for e to the x and for sine of x. So we're going to say that e to the sine x is equal to, well, the expansion of sine of x, the first 2 terms are x minus x cubed over 3 factorial. So this is e to the, and then we expand, we put the expansion in here, x minus x cubed over 3 factorial. And we could go on, but the next term is x to the power of 5, and we'll find that we're actually not going to need that. So then we can say that this is e to the x times e to the minus x cubed over, let's expand that 3 factorial to 6. And now we can use the expansion of e to the x on both of these. So we can say that this is the expansion of e to the x, which is, we've got it here, 1 plus x plus x squared over 2 plus x cubed over 6, 3 factorial, which is 6, plus x to the power of 4 over 24, that's 4 factorial. Now we don't need to go further than that, as it turns out. We can also expand this, e to the minus x cubed over 6. We just get 1 plus minus x cubed over 6, so minus x cubed over 6. And we don't need to go further than that because the next term would have x to the power of 5 in. So when we multiply out these brackets, we're just going to get an x to the power of 5 when we multiply by 1. And we know we can disregard anything with powers of x greater than 4. So let's just put a dot, dot, dot in there. And now all we need to do is multiply out these brackets. We've only got 2 terms here, so this is not too hard to do. So this 1 times all of this is 1 plus x squared over 2 plus x cubed over 6 plus x to the power of 4 over 24. And then we've got to do this times all of this. Well, let's start here. Minus x cubed, 1 times minus x cubed over 6. So we're going to say that's minus x cubed over 6. X times this is minus x to the power of 4 over 6. And we don't need to consider any terms higher than that, so we don't need to worry about this x cubed times that x squared, because it's going to be x to the power of 5. So we're ignoring terms higher than x to the power of 4. So we can say that this is now 1 plus x squared over 2. These 2 terms cancel out. X cubed over 6 minus x cubed over 6, so we've got nothing in terms of x cubed. And here, minus x to the power of 4 over 6 plus x to the 4 over 24 is x to the power of 4 over 8, so minus x to the power of 4 over 8. And then we are done here. So this is one of those ones that I mentioned in the previous examples where you find that a term cancels out. So if it had asked us to find the first 5 terms, for example, then actually we would have had to have gone further than the 5 terms we had here to get the x to the power of 5 or x to the power of 6 term here. I'm not sure what it would be actually. Okay, so that's it for using the Maclaurin's expansions that are in the formula book to generate Maclaurin expansions for more complex, or to generate series expansions for more complex expressions. Thank you for listening, and we'll finish there.